Okay. We apply what we did previously. Just bullet points. And there's some conceptual things that need to be written out here. But some of the details got written out much better. Okay, well, the polar coordinates have the unit circle. That is right into the unit circle. And so picture the unit circle in the middle of the interval, which is the area of the unit circle, which is pi because there's pi r squared r one. Okay. We want to partition this. Because maybe we don't want just the area, we want to move inertia. Okay, maybe we want the mass if we have a test for the inertia. Okay. We do it all if we can write down the partition. Okay, so first of all, please start with that. How do you describe this circle in terms of polar coordinates, just so we orient to the polar coordinates. Okay, what's the minimum and maximum possible amount of r at a point on this circle? 1, but clearly r can't be bigger than 1 or you're outside of the circle. Clearly r could be 0 because the origin is there, and r can't be less than 0. Negative distance. R actually could be less than 0, but we're going to combine r from 0 and the maximum possible. So 0 less than equal, r less than equal 1. 0. Okay, what about theta? Now, theta is a theta. It can be anywhere from here to here. In typical theta, that's one out. Theta, the typical point. There's the r and the theta. Theta can clearly be anything from 0 up to 2 pi. Now, this is written down. 0 less than or equal to theta, less than or equal to 2 pi. But of course, the 2 pi point is the same as the 0 point. So, and the coordinate of any point on this green line, the theta coordinate could be 0, it could be 2 pi. We don't want the same coordinate here twice within our limits, so we use a less than 2 pi. Less than equal to theta, less than 2 pi. Otherwise, every point on this green line will be represented twice. Now that wouldn't hurt anything because the area of that line is 0 anyway. But in some cases, we want to or include it. Okay. Now, those are the intervals of dot partition. R goes from 0 to 1, theta goes from 0 to 2 pi, they give you a whole circle. There's no question how anybody got through the problem stuff. They ample use of these concepts and didn't understand the concepts. Probably done by imitation with examples. That's one step, but you got to go beyond that. You got to understand the entire picture of the entire principle, the entire problem. So that's the word. Okay. So we partition the interval from 0 to 1, and there's your usual partition. Now, in class, what are the right, the RI star in between here and here? That's not part of the partition. You write that separately. But the partition's written out very well. R naught, less than, you probably have less than R1, and less than these knots. Okay? Just establish pattern. Okay, so there it is. Now there's some dots in there. Okay, and then we say Ri minus 1, Ri, typical, identical, has sample 1 Ri star. Okay, well that's good. What about theta? Theta can go from 0 to 2 pi. What I said before about 0 equals theta, and the last theta equal to 2 pi doesn't really work here with theta. Less than, it doesn't. Okay. So the partition starts at theta naught, which is 0. It ends at some theta m, which is 2 pi, except now this is the theta partition that corresponds to the ith interval of the arc of the arc, the ith subinterval of the partition of the arc. Okay. And so we're going to have to use a subscript of I on every one of these symbols. In our typical interval is theta ij minus 1 less than theta ij star less than theta ij. That was not less than reason. The sample point is always inside cost okay. So now in the sketch, the typical increment with the sample. And well, Ri minus 1 less than Ri star less than Ri. Where's that increment on the sample? Well, that means your R is going to be bigger than Ri minus 1 and less than Ri. Where is, and we have some difficulty because again, there are concepts that one would assume everybody has and doesn't know. It doesn't happen. And I'm kind of in a learning process myself of what happens because maybe you should know something. Okay, fine. Oh. I like my assignments better than web assignments. The web assignment is used correctly. And students improve another challenge. Have good results. Okay. So far, that's been okay. Anyhow, if R equals Ri minus 1, where is R equals Ri minus 1 in the picture? Well, R equals some number, like R equals 1/2, would be a circle with radius 1/2, wouldn't it? And when I pose it like that, that's what it means. Okay, and that made the extension to, okay, if R equals Ri minus 1, we'll just call that your Ri minus 1. And then Ri is bigger than Ri minus 1, so R equals Ri here. And then it's like it's shaded, but here's your region, Ri minus 1 less than Ri. And that would be this region here. R equals Ri, R equals Ri minus 1. What about theta between theta ij minus 1 and theta ij? Not that pretty, because everybody's wanting to right way. Okay, and when we're talking about R, that's not what you want to do. Constant R. Okay, between two constant theta gives you just a line emanating out of the origin. Okay, so theta equals theta ij minus 1 would be this. Theta equals theta ij. Well, theta ij is bigger than theta ij minus 1. So we do the right. And you have this well. And that's nicely drawn. Okay, it's a nice size. So now we can draw our ij increment. Now we want to get the area of the ij. Let's say we're just trying to get area. But of course, trying to get mass, given mass density, we have to have the area multiplied by mass. Try to do inertia. We have to have the area multiplied by mass density. And then by square the distance from your axis of rotation. Okay. So here we are with our ij. Okay, just enlargement of this. There's the question, what are the dimensions and sigma? Well, showcase very quickly. This blank here is RI minus RI minus 1, which is your delta RI. And this is the same, because of course, this side goes between this circle and this circle. This side goes between this circle and this circle. Both circles are centered at the same point, so figures are just the same. So that's easy. Okay. And the other should be easy if we understand what gradients are. So, arcs, so on, circles, and the angle. But that's always kind of challenging. And it is now the few hints we actually, class actually left. So that's nice progress. Okay, so we have, we're going to postulate an R equal Ri star, where R equals Ri star. So here's the R, here's your sample point, Ri star, beta adjacent. This is the arc of the circle centered below you that passes through that point. As we shrink the delta R's and the betas, this thing is going to shrink down to where this arc and this arc aren't much different. We have a very small delta theta, that's going to happen. And a very small delta R. That's going to be the case. And of course, then we're going to sample, we're going to denote that they be approximate with both of these by the length of this arc. Now, another thing is, as we shrink delta theta down, these three arcs are all going to approach straight arcs. You know, we're on the arc of a sphere. Okay, we don't see the spherical nature of the Earth because we're only viewing a very small piece of arc, unless we go up very high. SpaceX. Okay. If you have enough money, you can actually do it. Okay. So anyhow, we should understand this will approach a straight line, this will approach a straight line, this will approach a straight line. If we write down this arc distance, then we have the approximate length of that straight line. And also, as everything shrinks down, these are arcs of the circle, these are radial lines, so these are perpendicular to the circle. That wasn't drawn that way, it's faster than that. I've drawn it still. But a good accurate drawing, shows you pretty clearly the geometry situation. You want to spot that. Because it makes you think of things you can otherwise think about. Like things in solving the problem or something. Okay, so anyhow, we have our delta Ri, and now I say that this is Ri star delta theta. Why would I say that? Well, it's because back to the definition of gradient, probably would have come to the arc distance. Okay, a radian is the angle where the arc distance is equal to the radius of the circle. So that a fraction of the radian, which is what your delta theta is, and that should be the delta theta I delta theta being a fraction of the radian, then this is going to be the fraction of the radius. So we have 1,000 radian. The arc distance is 1,000 of the radius. Very simple. You can memorize all the formulas you want. You have one piece of paper. If you don't understand that, you don't understand it. Okay? Now, we go through the phase and we don't understand what we're doing, but we want to think about whatever we're imitating to the point where we don't have to do it by imitation. That's the ideal. If you're good at imitating, you pretty much get through the course like this. But you can't really nail it. And you can't really understand it. Really use it. Get by, but you're not going to not going to really be monitored. Okay. So anyhow, the arc length, and I wrote that down, delta, theta IJ minus theta RJ minus 1 times RI stop. This being your delta plate. Okay, so this is your RI stop. Delta theta IJ. And that's what we have labeled here. So now we understand that as everything shrinks down, and then these angles are all right angles throughout, whether we shrink them or not, because they're radial lines, and these are in circle. But these approach rectangles, and what are the dimensions of the rectangle? Well, I said, so delta IJ is what? That's what was down. That was good. Okay. This, which is delta RI, times this, which is RI star delta theta IJ. So now what's the whole area? Well, there it is. Okay, we just sum up all these. J equals 1, and I equals 1. I equals 1 to n, J equals 1 to m sub I. Well, this same expression. Well, that approaches the interval. What's the interval? Well, I equals 1 to n, that's your R. And as I go from 1 to n, your increments, supplement, go from 0 to 1. So 0, this is 0 to 1. And your interval was from 0 to 5. In other words, as your J index goes from 1 to m sub I, your theta goes from 0 to 2, 5. You're going to look at the cover the whole region from 0 to 5. Take the limit as the RIs go to 0 and as the theta IJs go to 0. In such a way that RIs and RIs approaches the index, theta IJ goes to 0. To get the 0. That interval should give you the area of the circle. Well, do the integration, it's trivial. Okay, so we did it over here. Double integral and actually go away very quickly. Almost done. You know, this interval, and I derivative of this interval. Now the R doesn't vary. As stated, it could actually come out of there, it could be left there also. You got to get R theta evaluated from 0 to 5, which is going to be the y line. And that's going to be integrated with respect to R. You integrate R with respect to R, you get R squared over 2, 0 to 1, meaning 1/2. And you end up with pi R squared. Okay. From 0 to 1. And that comes out, it's our comes out 5. That's really a true. So that's exactly what it ought to be. Look at the area of circles, pi R squared. If R is 1, then you're going to get 5 R. Now, if we want the area of radius 4, if this is a circle of radius 4, then the limits of R would be from 0 to 4. Everything else would be the same, except we have 4 here. And that would give you a 4 when you get down to the interval. So we have 0 to 4, 0 to 9 bar beyond. And so, yeah, down it's 16 pi. Well, R squared, 4, 5 times 4, which is 16 pi. In general, interval from 0 to capital R. Capital R is the radius of the circle. And then 0 to 1 of R is negative R. Same rule as pi R squared. Right there is the notation. Also comment that you can break a circle into sectors and stack sectors like I've done here. Okay. If you make the sectors very tiny, with a small angle, then these arcs become almost straight lines. And you have half of the arcs on this side of the stack and half of the arcs on this side, which means you have half of the circumference here and This distance here is just going to be the radius. So you multiply half of 2 pi r, half the circumference by radius, you get pi r squared. Bruce figured that out a long time ago. They were very young. I don't know exactly. Okay. So there. There's something written up here, which was not a good idea. There's the process. So this is the process for setting up any interval. Interval for volume interval, 3 dimensionals, spherical coordinates, cylindrical coordinates, fluid coordinates. You can understand them in terms of this, and we always want us to do until you master the idea of partitioning and understand why it works. You want to set up all your intervals, like writing out partitions. Very straightforward. It's pretty much the same anytime you do it. The only hang up is the same thing you got to do. You just do this by invitation. You've got to figure out what your limits are. And often the limits are already established. So you might just think of the circle. What is this circle? It is a circle. You got all the side there for your limit. But if that's a full equation, then R would go from 0 to some phase. So we have to draw that region before you can see it. You have to figure out what the region are. Well, R would go from 0 to some phase. As we go, we just take a look at it. Because those are equivalent to the region. And all the same process. You're going to get circle, you're going to get it's going to be a circle, but radius won't have. And then what you got when you draw this, and you can work that out. Okay, well, got a class coming up. I'm going to have to tie this up. And your task, of course, is to tie up all of this chapter using as much detail in your thinking as you can and writing things down, and wrap it up as well as possible. And good luck with that. It's tough. But I think you're up to it. Might not get it all in the next few days, but you're about to get it.